Alrighty. Good morning, everybody. Welcome back to Calc 1. Plan for today is I have a double quiz for you, standards 11 and 12. And then we're going to start standard 13. We're going to look at initial value problems today. And then we'll segue from that into looking at motion problems involving acceleration, velocity, distance traveled on Monday. I've got my usual office hours later today at 11 and at 2. No office hours tomorrow, or Friday for that matter, because it will be fall break. I'm not assigning any new homework, but don't forget you do have homework due tonight and one due on Monday. Also, someone turned in a standard 10A quiz without their name on it. So if that is you, let me know after class. Or whenever. Think it's yours, Jeff?
Yeah.
How embarrassing. Ask me after class later. Let's see. I updated Canvas yesterday, so everyone's mastery totals on Canvas should be up to date. Let me know if you see any discrepancies. And with that, a math major once was given the following question on a physics exam. You're given an accurate barometer. How can you use it to determine the height of a skyscraper? Student answered, go to the top floor, tie a long piece of string to the barometer, lower it until it touches the ground, and then measure the length of the string. Professor, who was unhappy with this answer, went up to the student after class and says, look, can you give me another method, one that demonstrates your knowledge of physics? Sure. Go to the top floor, drop the barometer, measure how long it takes to hit the ground. That's not what I had in mind. Would you like to try again? Okay, says the student. Make a pendulum of the barometer, measure its period at the bottom, and compare it to its period at the top. Try again, the professor demanded. Measure the length of the barometer, mount it vertically on the ground on a sunny day, measure its shadow, then compare it to the shadow of the skyscraper? This is ludicrous, says the professor. Again. Walk up the stairs, use the barometer as a ruler to measure the height of all the walls in the stairwell? Last chance, young man. Find where the janitor lives, knock on his door and say, please, if I give you this barometer, will you tell me the height of the skyscraper? Part of the story is, there's a lot of interesting ways to solve the problem. All right, any questions or comments before I pass out this quiz? So one quick comment on this quiz. This quiz, as promised, is sort of a double standard 11, standard 12 quiz. It's just the first page is standard 11, second page is the standard 12, and you will get graded separately on each. So with that, let's go ahead and do the quiz for today. He's hiding on it.
Oh, thank you. From the angle I thought it was a little half.
Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Pass your quizzes in, please.
No, I don't think that. Is it yours?
Oh, no. I think it passed. So I asked her, like, and I might leave myself.
Break that, you
Like,
can't
her.
make it 3T to the 0.
Is that yours? Hold on. I'm gonna keep this for another class just so I can give you credit for it.
I already have something in place.
Just so I remember.
Like last year.
Did I pass it?
Yeah.
Forgot, like,
Story and stuff. I'll find out. I just have too much stuff.
how did I do that with Ryan?
No, what I'm saying is like, don't feel bad, because like I have the like.
It's not a fun friendly. Alrighty, let's come back together.
I drew the piecewise, too.
So So our ultimate goal in this coming standard is going to be to look at a variety of problems where we know, say, the acceleration and maybe velocity of a moving object, and we want to say something about what distance it's traveled. So in other words, we've reached the sort of turning point in the semester with this standard. And that in this standard, we're going to move away from how do we differentiate / integrate things. Because at this point, we've kind of talked about all the different types of functions we're going to be differentiating and integrating over the course of the semester. And instead, we're going to be kind of focusing instead on what can we do with derivatives / integrals. In other words, how do they kind of help us solve some real-world type of problems? That'll take us through the next several standards into linearizations, optimization, first and second derivative tests. So in this standard, I'm going to start off by talking about initial value problems. So to start, I want to look at this question. If f prime of x is 2x minus 4, what could f of x be? So in other words, if we don't have a formula for our original function, but we know what its derivative is, specifically that f prime of x is 2x minus 4, what could f of x possibly be equal to in this case? See it?
X squared minus 4x like plus 1.
Okay. F of x equals x squared minus 4x plus 1. Let's see, I think that would certainly be a function whose derivative is 2x minus 4. Any other functions? Well?
F of x equals x squared minus 4x.
Okay. Zach?
X squared minus 4x plus 33.
X squared minus 4x plus 33. I wonder where 33 came from.
Just came in my head. Pop.
Well, I'll talk about my sarcasm here in a few minutes. Is there a general pattern to the sort of functions that f of x could look like? Riley, I see you nodding.
The main function that x squared minus 4x is always going to be there, and then just with different constants.
Yeah, so in other words, f of x has to be equal to x squared minus 4x plus c for some constant c. And this is something like, basically, we can integrate 2x minus 4 to find all the possible functions, the family of functions, because mathematicians love their families. Family of functions whose derivative is all the same, 2x minus 4, is going to be any function, is going to be made up of all functions of this form, where f of x has to be equal to x squared minus 4x plus c, for some constant c. What can we say graphically about all these functions? Specifically, what do all of these functions have in common when we look at a graph, and what's going to be different? Yeah?
They will all have the same slope and general properties.
Okay, yeah, they're all going to have the same slope at each point. What's going to be different about the graphs if we were to look at, say, different values, plugging in different values of c? Right?
Because they're just going to be shifted up or down on the graph.
Yes.
Maybe side to side.
I don't think side to side. I think plugging in plus c though is going to result in having functions that have exactly the same shape but are vertically shifted upwards or downwards. So for instance, we give these functions, let's say, names. For the sake of argument, I'm going to change this one to a minus 10. I think our f2 of x is going to look something like this. Let's see, it's a parabola opening upwards. That's going to equal 0 at x equals 0 or x equals 4. So our f2 of x is going to look something like this. If we wanted to graph f1 of x, it would be the same function, but every y value is going to be shifted down 10 units. So it's going to look something like this instead. And if we wanted to look at, say, f3 of x, everything's going to be shifted up 33 units from f2 of x. So it'll end up looking like this. So what's going to happen, though, in other words, is that all functions sharing the same derivative as Riley pointed out, are going to look exactly the same as each other. They're just going to be shifted vertically up and down by whatever value your c is. Because this value of c at the end is just going to give a constant shift in what the y coordinates of all your points are going to look like. So all functions sharing the same f prime of x are identical graphically except they've been shifted vertically some amount. So that tells us a relationship between all the functions in this family. If your derivative is 2x minus 4, you have to be basically this parabola right here shifted upwards or downwards some distance, but not to the left or right. If it's to the left or right, it'd be a different function and would have a different derivative. Any questions or comments about that? So what I want to do now is I want to add a wrinkle to the problem and say, let's say we don't just know what f prime of x is. Let's see if we know that f prime of x is 2x minus 4. And let's say we also know that f of 1 is 30. What can f of x possibly be? So now, we not only want to find a function whose derivative is 2x minus 4, meaning it'll have to be a function that looks something like this, x squared minus 4x plus some constant value. But we also want to ask the question of how can we find a function in that family that also has to satisfy the condition that f of 1 is equal to 30? That if we were to plug in 1 for x, we would get a y value of 30. Because I don't think every function of this form is going to have that f of 1 equals 30 property to it. They'll all have the same derivative of 2x minus 4, but the f of 1 equals 30 is going to add a little bit of a wrinkle into things. Any ideas how we could find what f of x would have to look like if we wanted it to satisfy this new condition in addition to what we already said about its derivative? Anna?
You could set the equation x squared minus 4x plus c equals 30 and put 1 for x and then solve for c.
Ooh, okay. So we know from this condition that since f prime of x is 2x minus 4, we know that f of x has to be x squared minus 4x plus c for some constant c. And what you propose, Anna, that we do is say, if we can find what c should be equal to because if we plug in 1 for x, it should come out to 30. So you propose we just plug 1 in for x in this equation, set it equal to 30, and solve for c?
Yeah.
I like it. So we can say since f of 1 equals 30, we're going to know that f of 1, which if according to this formula should be 1 squared minus 4 times 1 plus c, should come out to 30. I think I agree with that. F of 1 is whatever we get when we plug 1 in for x here. But it's also 30, so we should be able to set these two expressions equal to each other. And then, how can we solve this equation for c? Is it?
Do 1 minus 4. And then that's -3. And then you add -3 to both sides. Or add +3 to both sides to get 33 equals c.
Yeah, so if we simplify this left-hand side, we'll get that -3 plus c is 30. And then you propose we add 3 to both sides to get c equals 33. Interesting. So what's going to be our final answer then for what could f of x be that would both satisfy f prime of x is 2x minus 4 and f of 1 equals 30? That?
F of x equals x squared minus 4x plus 30.
X squared minus 4x plus, what did you say?
33, sorry.
Plus 33. I like it. Oh, hey, it's our f3 of x, the one that Zach proposed earlier.
Crazy.
Say what?
Crazy.
It's a crazy, what a crazy coincidental world we live in here. So, here's the moral of the story. We have infinitely many, there's infinitely many functions whose derivative is 2x minus 4. Because any function of the form x squared minus 4x plus some constant would fit the job. And there's infinitely many values we could plug in for c that wouldn't change the derivative at all, because any constant is going to have a derivative of 0 and not affect the derivative. So there's infinitely many functions up here. That'll have a derivative of 2x minus 4, with these three functions right here being 3 of those functions. As it turns out, though, that when we add this new wrinkle into the problem, that we want f of 1 to be equal to 30, all of a sudden we found only one function that fit the bill. F3 of x from over on the left-hand border. Because out of these infinitely many parabolas that are all shaped exactly the same, shifted up and down, only one of those is going to pass through the point 1, 30. That only one of those satisfies, in other words, if you plug in 1 for x, you'll get a y value of 30. I could keep drawing parabolas in this family all day long, and none of them, other than this red one here, are going to pass through this point 1, 30. And so this type of problem, we typically are going to call an initial value problem. I think I wrote in your packet up at the top of the front page. Where an initial value problem is basically one where we're given information about the derivative of f of x. In this case, we knew what f prime of x was, and we're given what's called an initial value. So this was our initial value right here, which is f of 1 equals 30, where an initial value is typically just, one output from the original function. In this case, f of 1 equals 30. That's something that we knew, or that we were given. That was sort of our extra piece of information, our initial value of the function. And with this knowledge of what's the derivative and what's an initial value, we were able to uniquely find a function that satisfies both of these conditions. Our knowledge of f prime of x told us the basic shape of the graph, kind of what the slope was at every point. And that gave us infinitely many parabolas our original function could have been. And then using this initial value here, f of 1 equals 30, we were able to pick out a single parabola from this family that satisfied both properties. Any questions or comments about what we just did? In that case, I have two more initial value problems for you on the second page. I'd like you to take a couple minutes, and as always, you're welcome to talk to your neighbors or to ask me questions. See if you can solve these other two initial value problems. All right, give you information about a g of x, or I want you to find a g of x and an h of t function, using kind of the same technique of using derivative and initial value, what must initial function be? And as a hint, if you're not sure how to find a general formula for g of x or h of t without using your initial conditions, you might want to use some of our integration techniques from the last couple of standards to go from g prime to g or h prime to h. Don't forget, we said that one of our rules for integration, so that would be if you wanted to integrate a power function using the reverse power rule, like 2 to the 4th. So for something like 4 to the t, where your variable is the exponent, I think you needed to use the rule from last standard that's integrating a to the t. Some constant to the, say, t power will give us that divided by the natural log of your constant.
I got 9 minus 4 divided by -4.
My lack of knowledge.
It would be 6.
You look at it and realize it's not a nice number, and there's no way to really simplify that one.
Okay.
Just looking at it, let me look at it.
Hey, calm down.
It keeps telling me it's not 6, and I believe it, but I'm trying to see why it's 3.
Hey, give it.
Shut up! It's not 3, it's 2.
All right, guys, give him a chance to think about it. Okay.
Because 2 times 3 is 6. Divided by 2 is 3.
We figured it out. We were just
No,
using that.
no.
That was AT times.
No.
This is that's the during.
You have it right. You
That
have
was
it
right,
right.
okay.
Yeah.
It's 2. You have it right, Josh. You have it 2.
We want to.
2's right.
Yeah, you're absolutely right. If we differentiate, we multiply by a natural log of constant, which means when we integrate, we have to do the opposite, which is to divide by.
Today I'm gonna say.
You're a hot mess. That's
I am. I'm on like for the past 2 days combined. I'm on like 5 hours of sleep. 5 hours of sleep. Just to,
That's not healthy.
I know. I've been grinding on a paper just to get the feedback back, basically saying, yeah, it's not what I'm looking for. So, not that it's trash. It's just there's some work that needs to be done. But to do it at 5 o'clock today, she did not say trash.
thought you said.
Yeah, I only got about 3 hours of sleep last night. It's
Or
it's not good.
why? There's no reason.
There's no reason for what.
You get 3 hours of sleep.
There's health-related reasons, and academic-related reasons, and poor life choices-related reasons. And a combination thereof can do a whammy on your health.
That is so past my bedtime.
YouTube's killer, man. That's what gets me. That's
I
why.
was gonna go back.
There's also 8:45 classes you have to get ready for.
I don't know, the truth is, you could have Netflix in the corner of your phone while you
room
watch
at
it.
2:00 in the morning, and so I woke up. She was in the room.
The last
Like,
two nights.
what the?
2 to the 3 halves.
Okay.
That's what I said. Joshy boy.
I was setting myself up for adoption.
Joshy
It's
boy.
not nice, it's scary, and it's very hard to simplify.
I do not.
That's just gonna be
Subtract it all
two.
over,
Because
and equals that.
anything it's gonna be 1.
11 minus 2.
And then I stood, that'd be,
So I'm gonna take math
2
and
minus
math.
9.
So,
And I don't.
Because I know I'm
He
gonna
wants to
be
go
able to
to
sleep.
Yeah.
Like, there's no way I'm not up totally asleep.
My sister has an exam tomorrow, so
What, is your sister at school?
she's in the.
why do I keep on?
Oh,
Yeah. I'm like,
why would you wanna do that?
I don't
It's like
know.
so many years and then residency.
yeah, she's.
It's like 8 years of school.
She said that she just didn't want to like class like a job yet.
Okay, let's come back together as a class. And
8 years of school.
looking around, it looks like you all are making good headway into the first one. So I think it'd be good to talk about the second one as a class, where we know what h prime of t is, that it's 3 square root of t plus 4 to the t. We're also given an initial value, h of 1 again, that h of 1 is 11. And we want to find what h of t has to be equal to. What do y'all think? How can we get started on this one? Josh, what was the first thing you tried?
I just made it 3t to the 1/2 plus 4t.
Okay, so you took this top one and you rewrote square root of t is t to the 1/2. Okay. Ooh, okay. So if we integrate, we'll find a general formula for what h of t could look like. I'm on board. Rachel, were you able to integrate this one?
Yes, I got h of t equals 2t to the 3/2 plus 4 to the t over natural log of 4 plus c.
Like that? Let's see, if we differentiated this, we get 6/2 t to the 1/2. 6/2 is 3, so 3t to the 1/2. I like that first one. The derivative of this is 4 to the t over natural log of 4 times natural log of 4, so 4 to the t. Derivative of c goes bye-bye. And yeah, I like it. So I think this will give us a good, nice general form for what our h of t should look like. Where just knowing what h prime of t is, we end up with still infinitely many functions, but we know what all those functions look like other than their constant term. So how can we solve for our constant term in this one? Alan?
You just plug in the point that they gave you for y and x, so for c.
Say that again? So we plug in the initial point and then,
To solve for c.
oh, to solve for c? Sounds good. So here, it sounds like Helen, you want to use the fact that h of 1 equals 11, and similar to what we did over here, plug in 1 for t, set the equation equal to 11, and solve for c. I like it. So since h of 1 equals 11, that's going to tell us that 2 times 1 to the 3/2 plus 4 to the 1 over natural log of 4 plus c should come out equal to 11. So let's see. what is 2 times 1 to the 3/2 gonna be?
2.
Taking something to the 3/2 is scary, but since we're plugging in 1 to the 3/2 is just 1. It's like 1 to any power is 1. So we get 2. 4 to the first is gonna be 4 to the first is just 4, so this becomes 2 plus 4 over a natural log of 4 plus c is equal to 11. How can we solve this equation? Let's see, someone other than Josh or Zach, or Rachel, how can we solve this one for c? Hannah?
You can just subtract 2 plus 4 over natural log of 4 from that side.
Okay, so subtract 2 from both sides.
Yeah, and then subtract, yes.
Or to get c by itself. Okay, if we do that, what are we gonna get?
9 minus 4 over the natural log of 4.
Yeah, I think so. If we subtract 2 from both sides, the right-hand side becomes 9. If we subtract 4 over natural log of 4 from both sides, we get 9 minus 4 over natural log of 4. So, Hannah, what's going to be our final answer for what h of t has to be equal to in this case?
2t to the power of 1.5 plus 4t over natural log of 4 plus 9 minus 4 over natural log of 4.
Like that?
Yeah.
I like it. Yeah, same basic process as what we ended up doing over here. We used our knowledge of what the derivative is to find a general formula for our original function h of t, where just knowing what the derivative is, we have this plus c at the end that we can't necessarily solve for. But then we used our initial value of h of 1 equals 11, and by plugging that in and to our function, h of 1, and setting that equal to 11, we were able to solve for our constant c. And so our infinitely many functions that we have over here became just a single function that satisfied the condition of h prime is 3 root t plus 4 to the t, and h of 1 is equal to 11. Same basic process as what we did here. We were able to find only a single function in the end that fit the bill by using our knowledge of the original function's derivative and an initial value. This one, the functions were a little bit harder. Our constant term was a little bit less nice. I don't think we can really simplify this at all. I mean, we could combine this into these two terms into a single fraction if we want, but 4 over natural log of 4 is not a nice number. There's no way to make that look prettier. So I think I'm going to leave my answer like this. Any questions or comments? All right. How are we doing? Great. Pull out the big guns. Look at this next page. Let's say we know 3 things about a function f of x this time. Let's say we know f double prime of x is 60x. F prime of 1 is equal to 10. And f of 2 is equal to 41. Time out, Dr. Gerstle. What is this f double prime you speak of? We haven't seen this. This is going to be our first time encountering this. But when you see something like f double prime of x, what that means, what that's called is the second derivative of f of x. And the idea is that f double prime of x is going to be what you get if you differentiate twice. So in other words, it's going to be the derivative of your derivative. And as we'll see in the next several standards, f double prime of x can tell you some interesting stuff about your initial function, just like how f prime of x can. And so if we want just a quick example over to the side, f of x is, let's say, x cubed minus 5x plus 1. What would f prime of x be? Laura?
3x squared minus 5.
Yeah, it's going to be 3x squared minus 5 if we differentiate. F double prime of x is going to be what we get if we were to differentiate again. So let's see. Will, what would we get if we differentiated f prime of x this time?
If I differentiated it,
Yeah, if we just differentiate 3x squared minus 5.
yeah, you get 6x.
Yep. So when we take f double prime of x, that just means differentiate and then differentiate again. And differentiating the second time, you'll typically end up using some various combination of the same rules you did with the original time. So here, if we look at this problem, we're given 3 pieces of information this time. We're given a formula for f double prime of x. We're given an initial value for f prime of x, and we're going to have an initial value for f of x as well. And our goal is going to be to find a formula for f of x based on all of these pieces of information. So, similar in concept to the last few problems we've done, it's a little bit trickier, because instead of just having a formula for the first derivative and an initial value for our original function, now we have a formula for our second derivative and 2 initial values, one for f prime and one for f. So what do you think we can do with this one? Josh, any ideas?
You'd have to do one integration, solve for f prime, then do another and solve for f of x.
Okay, so you want to start by integrating f double prime of x to find a formula for f prime,
Yeah.
and then repeat the process?
Sure.
All right, let's do that. So, since f double prime of x is equal to 60x, I think that's going to tell us that our first derivative, f prime of x, should be an antiderivative of f double prime in order for the derivative of f prime to be f double prime. And let's see, Vera, what would we get if we integrated 60x?
We would get 30x squared plus
30x squared plus some constant? I like it. Yeah, so in other words, this first piece of information, f double prime of x equals 60x, is going to tell us something about f prime of x. Namely that f prime of x is 30x squared plus some constant term. All right, neato burrito. Where can we go from here? When?
You can set f prime of x equal to 10 and plug in 1 for x.
Okay,
Solve for c.
so it sounds like you want to use the second piece of information here to solve for c. Sounds reasonable to me. So if we do that, we'll get f prime of 1, which is 30 times 1 squared plus c, should be equal to 10. Use our initial value for f prime here. And what do we get when we solve this equation for C? Rachel?
Negative 20.
Let's see, it's going to become 30 plus C equals 10. We subtract 30 from both sides. We'll get that C has to be equal to negative 20. Sounds reasonable. And I think that's then going to tell us exactly what f prime of x has to be. That f prime of x is going to need to be 30x squared minus 20. That's the only formula f prime of x can have if we want that f double prime of x is 60x and that f prime of 1 is equal to 10. We have a problem though, in that the problem didn't ask us to find f prime of x. The problem asked us to find f of x instead. So how can we go through and actually find f of x instead of just plain old f prime of x, Mackenzie?
Take the integral of f prime of x, which is 30 x squared.
Ooh, so you want to integrate a second time, this time to go from a formula for f prime to a formula for our original f? I like it. Let's give it a try. So if we do that, this will tell us that f of x should be an antiderivative of 30x squared minus 20. What are we going to get if we integrate 30x squared minus 20? Look at
10x cubed minus 20x plus 1, or plus c.
10x cubed minus 20x plus a constant. I like it. Because let's see, if we differentiate that, we would get 30x squared minus 20. One small thing, I don't want to use c for our constant term because we already used the variable c earlier in the problem for the constant term on the end of f prime of x. So in order to avoid using the same variable for multiple things, I'm going to call it plus d instead. Just use a second variable for our second constant term that's kind of popping up over the course of the problem. Because otherwise we might get confused and say, oh, we already found c. c is negative 20. Well, this constant was negative 20. This constant maybe not so much. Okay. Mackenzie, I like your idea. This allowed us to find a general formula for what our f of x should be equal to. And finally, what can we do that's going to allow us to solve for the variable, or solve for our constant term d here? I think there's one more piece of information in our original problem that we haven't used yet that might be helpful. So if we want to solve for d, what can we do? Riley?
Plug in 2 for x and set it equal to 41.
I like it. So in other words, you're proposing that we use our third piece of information, which we haven't used yet, that an initial value for f of x is that f of 2 equals 41. And so now we have something where if we plug in 2 for x, set it equal to 41, we should be able to solve for d. Sounds good. So if we do that, we'll get that f of 2 is going to be equal to, what, 10 times 2 cubed minus 20 times 2 plus d should be equal to 41. Emily, what is 10 times, how can we simplify this left-hand side?
You would get 40, so then you would subtract 40.
Okay, so this is gonna come out to 2 cubed is 8 times 10 is 80. Minus 40 plus d equals 41. And when we combine the 80 and minus 40, we would get 40 plus d is 41. And how did you propose we solve for d there?
We subtract 40 from each side.
And what's that gonna give us? Yeah. So one last time, we use our initial value here to say that d has to be equal to 1 if f of 2 is to be 41. And so then, who haven't I called on yet? Elise, what's going to be our final answer for what f of x should be equal to here?
It's gonna be 10x cubed minus 20x.
10x cubed minus 20x plus 1. I like it. This one was a bit of a trickier problem in that we weren't just given an f prime of x and a single initial value for f and told to solve for f. We had two initial values, one for f prime, one for f, and we knew what our second derivative was equal to. And so essentially then this became two different initial value problems in one. And that we used our formula for f double prime and our initial value for f prime to find a general formula for f prime of x. These two pieces of information told us that f prime of x was 30x squared minus 20. And then we integrated that function and used our initial value for f of x to find what f of x should be equal to, specifically that it was 10x cubed minus 20x plus 1. And I think we needed all three of these pieces of information because we needed f double prime to have something we could start integrating. We needed this f prime of 1 equals 10 to solve for this constant term c, to get c equals negative 20. And finally, we needed f of 2 equals 41 to solve for this constant term d, this other constant term, which gave us that d equals 1, and then that allowed us to finally say f of x has to be this cubic degree 3 function, 10x cubed minus 20x plus 1. That's the only function whose second derivative is 60x, that if you plug in 1 into the first derivative, you get 10, and if you plug in 2 into the original function, you get 41. Sort of a double whammy of a problem. Any questions or comments? Yes, Alan?
So for the first derivative, you plug in the point 1 and 10. You even really have to plug in that point because it's going to be a constant number anyway, so it'll just go to 0.
Well, not necessarily, because if we were to take this function and I were to ask you find f prime of 1, you're not going to start by plugging in 1 and then differentiate, which would give us 0. We would differentiate first, which would give us 30x squared minus 20, and then plug in 1. And so that wouldn't necessarily have to come out to 0 when we take f prime of 1. Since the order in which we do it is differentiate, then plug in 1, if we did the opposite, if we plugged in 1 first, then you're right, it would just come out to 0. Not necessarily. All right. Have a good fall break, everybody. When we come back, we're going to talk about Wile E. Coyote and shooting cannonballs and how can this basic process be applied to solving some motion physics-y type problems. Hope you all have a good break. I'll see you all on Monday.
The classic blunder.